Okay, so where we left off was we said we were going to take a look at some of the problems from the textbook. And the first one that we're going to look at is question 14.9. It says, for each of the following compounds, identify whether it is consistent with the structure of an alcohol or a carboxylic acid or neither. So if you look at an alcohol, so I'll just pencil it in over here, okay? For an alcohol, okay, there's a couple of things that we could look for with an alcohol. We could look between 36, I'll just write roughly 3650 to 3200. We see broad OH stretching. And remember it's broadened because of hydrogen bonding. And then keep in mind that in an alcohol, there's also the bond between the carbon and the oxygen, and that is also pertinent. That's between 1250 and 1000. So that is going to be our CO bond stretching. Put that in here like that. Okay, now for a carboxylic acid, let's put in the pertinent stretching. So carboxylic acid. So for a carboxylic acid, there's three of them that are going to be relevant. So the first one, so we'll just write the functional group here. The first one, of course, is going to be the oxygen-hydrogen stretching, which is very pronounced. So that's between 3,300 and 2,400 reciprocal centimeters, and that is broad OH. I'll just leave that like that. Then we have the carbonyl, which is at around 1710. 1700 is close enough though, so we'll say that that's the carbonyl. And then the carbon oxygen stretching is between 1320 and 1210. So that's the carbon oxygen stretch. So that would be this stretch here. Anyhow, so now that we know what we're looking for, if we look at, if we just take a look at all six of them kind of quickly, so there's A, B, C, D, E, and F. I mean, it becomes abundantly clear which ones are the carboxylic acids. Why can I say that? It's because whichever ones have these broad oxygen-hydrogen stretches, which go on forever, from 3,300 to 2,400. So you can see that here in this one. And then you also see it in B. So you see these very broad carbon-oxygen stretchings, or sorry, oxygen-hydrogen stretching. So you'd say this is the OH stretch, and I'll just put here carboxylic acid. And then with this one down here, I'll just label it over here, OH stretch from a carboxylic acid. So now that we know that those two are carboxylic acids, let's see if we can find the carbonyl. So for the one in C, you can see that the carbonyl is here. So we'll put carbonyl stretch like this. Now for the carbon oxygen stretch, it's between 1320 and 1210. So if we zoom in here, so if this is 11, 12, 13, 14. So I'm not sure exactly which one it is. You could even circle both of these and just say one of these must be the carbon oxygen stretch. And that's close enough for annotating our spectrum. If we go over to the other one, which was down here, okay, this one's a little more abundantly clear. This is our carbonyl stretch. And the only one that's pronounced down here would be this one. So this would be the carbon oxygen stretch. So those are for our two carboxylic acids. Now with the alcohol, we look for a broad stretch, but it's not nearly as pronounced for our oxygen-hydrogen stretching. And so I can see that we have an oxygen-hydrogen stretch in this one here for an alcohol. And then we also have it in this one here. Oops, let me trace that a little better. So it would be A and E are the two that have the alcohol stretching. So we have we'll put OH stretch, and you can put here alcohol, and then same thing here, OH stretch, alcohol. And then we can look for the carbon oxygen stretching between 1250 and 1000. So if we go into this one, 1000 is here, 1250 would be around here. So this would be the carbon oxygen stretch. So we'll just put CO stretch. And then for the other one, which is over here, so if 1000 is here and 1250 is around here, I would probably pick this one here. Okay, and if you're wondering if I picked this one, would I be wrong? Maybe, maybe not. I don't know. We'll say this one's the closest. So we'll put here carbon oxygen stretching. Okay, remember that's the fingerprint region. It's more difficult to read than the diagnostic region. Okay, and then you see that there's one in B and D, and neither of those are alcohols or carboxylic acids. How do we know that? There's no oxygen hydrogen stretching here, and there's no oxygen hydrogen stretching here. All right, the only thing that I can tell you about B, I'm not so sure about D, but looking at B, I can tell you that it's some kind of aromatic compound. And the reason that I can tell that is twofold. Well, maybe more than that even. If you draw a line at 3,000, okay, draw a line at 3, no, that's not very good, is it? Move this over. If we draw a line at 3,000, come on, ruler. Here, let's try this. No, still not good. Here we draw. Son of a gun. Really struggling to draw a line here. So let's try to do it like this. Let's do it by hand. If we draw a line at 3,000, no. Draw a line at 3,000. Something like that, okay? You can see here that around 3,100, we have sp2 hybridized carbon hydrogen stretching here that you would see in an aromatic ring, right? Because aromatic rings, right, have sp2 hybridized carbon hydrogen stretching. And then I told you that the carbon-carbon double bond stretching in an aromatic ring was 2 to 3 signals between 1400 and 1600, or around 1475 and 1600 actually. So maybe, you know, if this is 14 and this is 1600, you know, maybe these three here, you know, you would circle those and say those would be the carbon-carbon double bond stretching. And then I would say aromatic. Okay, I'd be sure to distinguish that from an alkene. And then if you remember, I mentioned overtones, which are between 1667 and 2000. That would be these things here. Those are aromatic overtones. So overtones. And those are just to give away that you have an aromatic ring. Anyhow, I won't go into any more detail on that. The next one is we're just trying to identify some functional groups. So I'm not going to write down all the signals this time. But this is question 14.10. So we've got a ketone, we've got an alcohol, we've got a carboxylic acid, we've got a primary amine, and then we've got a secondary amine. So we have those: ketone, alcohol, carboxylic acid, primary amine, and secondary amine. Why don't we look for the alcohol and the carboxylic acid first? Because we had those signals written down here. And so for the carboxylic acid, if you look at all 6 of these, I think the one that's the most abundantly clear is the carboxylic acid. So this would be your OH stretch from a carboxylic acid. This would be the carbonyl stretch. And then for the carbon oxygen, I would say it's probably this guy here. So this would be your carbon oxygen stretch for your carboxylic acid. The alcohol is probably the second most abundantly clear. The alcohol is this one here, which has broad stretching along here. So that would be your, this would be your OH stretch. We'll put here alcohol. And then your carbon oxygen stretch would be this one here. So this would be your CO stretch from your alcohol. All right, for the rest of them, I'm going to walk you through the amines, because remember, whether you're dealing with a primary amine, which has 2 stretches, or a secondary amine, which only has 1 stretch, okay? Remember that nitrogen is not as electronegative as oxygen, and so the dipole is not going to be as strong. And so if you look at C and D, you can see that in the region for the amine stretching, which is around 3550 to 3250, so we'll put that in here. So we'll put 3550 to 3250 reciprocal centimeters. Okay, that's actually what we see here. It's kind of this broad stretching. It's not very big, but it is there, here, and here. Now, if we zoom in on, I'm going to do D first, okay? If you zoom in on D, you can actually see that there's a stretch here and a stretch here. So that comes from the symmetric and asymmetric stretching of the primary amine. And so this would be a primary amine. So just write NH like this. So that's the primary amine functional group. Okay. And then for our amines, we just look for those stretches. For the one in C, since it has only 1 stretch here, This would be the secondary amine, okay, because it's only got one nitrogen-hydrogen bond. Again, not as easy to see as a carboxylic acid or an alcohol because they're not nearly as pronounced, but they are there. And then the other functional group we were looking for is a ketone, and you probably picked up on this while I was talking, is that in A and E, both of those have a carbonyl stretch in them, but with no other functional group. So here we have a carbonyl of a ketone. Remember, a ketone was around 17, 15. If you zoom in here, this is 15, 16, 17. So yeah, that looks around 17, 15. And remember, these are approximate. So this is carbonyl stretching for a ketone. And if we look at this one over here, okay, we also see if this is 15, 16, 17, it's close enough that this is the carbonyl of a ketone. And there you have it. So we identified all the functional groups in these spectra. So again, the best way to get good at this is to practice it. It's the only way to master it. So let's try one more. And this one is matching the functional groups or lack thereof with the compound. If we look at the first compound, it's just a alkane. The next one is an alkene. This one has an alcohol. This one is a dicarboxylic acid, but we'll just put here carboxylic acid. This one is a primary amine. And then this one is an ester, okay? And I wanted to look at an ester with you before we move into mass spectrometry because esters are very interesting in that an ester has a carbonyl in it, okay? But usually the carbon-oxygen bond here, this bond, that is the single bond, is very strong. So we'll put here a strong stretch for this guy here. All right, so now that we've got that down, let's see if we can identify any low-hanging fruit. Well, if we look at those four, I think we can see the alcohol. And if we look at this one, the last two, E and F, if you're wondering, is this what I think it is in E, or is just it goes on forever, the stretching here? Okay, yes, you're absolutely correct. That's a carboxylic acid. Okay, so that it's huge. But this is the OH stretch of a carboxylic acid. This would be the carbonyl. So that would be the carbonyl. And as for the carbon-oxygen stretch, I would say it's probably this one here. So it's the strongest one in the region. So we'll just put carbon-oxygen stretch for this one here. The next one that's abundantly clear probably would be the alcohol, right? So we've figured out the carboxylic acid. So that would be this guy here. So we could put in, so this is called malonic acid. Anyhow, the next one is the alcohol. So we can see the alcohol, the broad oxygen hydrogen stretching here. So we would say this is our OH stretch. Okay, and this is our alcohol. So what's the structure? It's this guy here. There you go. And then this would be the carbon oxygen single bond. So CO stretch. All right, so we've got those two done. What else do we see here? We are looking for a we have an ester. So something else with a carbonyl in it. Well, if we look at everything else, the only thing else that has a carbonyl would be this one here. So if I circle in B, so you can see at around 1700, so an ester, it's usually around 1735. Let's zoom in. So if this is 15, 16, 17, yeah, that looks like about 1735. So this must be the carbonyl stretch, okay? And it's an ester. We'll just write the structure of the ester, which is this here. Okay, this compound is called ethyl butanoate. The name's neither here nor there, but you see how this carbon-oxygen stretch is strong. So this would be the CO stretch. All right, what else? We've covered those. I think I saw an amine in there somewhere. Yeah, so if I look down here, this is a secondary amine, or sorry, no, this is a primary amine, isn't it? So primary amine, right? So this is the NH stretch, right? And the primary amine that we had was, it's called butanamine. It's got 4 carbons, so 1, 2, 3, 4. So yeah, it's called butanamine. And then we have 2 left. So we've covered this one, this one, this one, and this one. Okay, so between the alkene and the alkane, well, hopefully you can see the A is the alkene, and we know 2 things from an alkene. We look for the weak carbon-carbon double bond stretch around 1630. So if this is 15, this is 16, this would be it. Okay, it's very weak, but this is the carbon-carbon double bond stretch of an alkene. And then over here at 3100, this is the sp2 hybridized carbon-hydrogen stretching of an alkene. And so the alkene, this is called 1-pentene, like that. And then the last one is this one here has no functional groups. Therefore, this would be pentane, the alkane. So there you go. We covered all of those problems and got a little practice in identifying some of the functional groups. Even an aromatic, I showed you in this one here in B. So again, there's a lot of practice required to master IR. So I would go into the announcements in our classes Canvas shell, and you'll see that there's 2 practice problem sets. And then I have the solutions to those. You can highly recommend giving those a try. All right. There we go. Is anybody